Welcome back everyone to Unit 3 Physics Note Video number 6. Today we are going to talk about gravity and what happens when things fall. Well, gravity, it's a force. So that's one important thing to remember, is that there is a force of gravity. And gravity pulls on objects that have mass. So if you have mass, and all pieces of matter do, anything with mass pulls on every other object with mass. And that force of attraction that exists there is called gravity. So gravity is one of the four fundamental forces in the universe. Remember, they are strong, weak, electromagnetic, and gravity. Well, electromagnetic force is the force of attraction that exists between positive and negative objects, for the most part. And gravity is the force of attraction that exists between all things with mass. There is still much mystery behind why gravity even exists in the first place. Why is there this force of attraction between things with mass? Now, the reason that I keep saying all things with mass is a little bit of a misconception that kids often come in to 8th grade with. They think that gravity is only the force of attraction that keeps you on the planet, that it's the planet's pull on you that keeps you from floating off into space, for example. But remember, you have mass as well, so you also exert a pull on the Earth. So the Earth pulls on you, you pull up on the Earth. Why doesn't the Earth stick to you instead of you sticking to the Earth? Well, it's because the Earth is much bigger than you. So the force of gravity that the Earth exudes on other objects is much larger, because it is much larger than you. If you were bigger than the Earth, then the Earth would stick to you instead of vice versa. If you would try to jump, you would actually push the Earth away. So we have this force of gravity, and it is affected by two things. So the actual strength of the gravity, the actual strength of this force, is dependent on the distance between the two materials, the distance between the two pieces of matter, and the size of their mass. So the farther apart the two objects are, the less gravity there is. So the further away you make two objects, the force of attraction will go down. So if you were to climb to the top of the highest mountain, there would be a slightly less pull of gravity on you than there would be if you were at sea level, and technically there would be even more of a pull of gravity on you if you were down in a deep cave, I suppose, because it would be measured from the center of the Earth. And likewise, if you were floating in the emptiness of space and there was a material next to you that had mass, there would be a force of attraction between the two of you, and you would slowly drift towards each other. But the further away you were from that object, the gravity, the pull of gravity would diminish a lot. The other factor that establishes how strong this force is mass. And the greater the mass, the stronger the pull. So the further away the distance, the less the pull. The greater the mass, the more the pull. And this was all figured out by Newton a very long time ago. The Earth has a specific force of gravity, and it is 9.8 meters per second squared. Notice that the force of gravity is given to you in the units of, that's correct, acceleration. So meters per second squared is an acceleration unit. That means the force of gravity is measured as an acceleration. To make things easier, to make estimation easier, to make the math easier, to make it easier punching things into the calculators and worrying less about decimal points, it is totally okay with me if you just round that off to 10. You can just say that the Earth's pull of gravity is 10 meters per second squared. As far as 8th grade physics goes, that's not going to change your answer all that much. Now, if I was counting on you to launch a projectile in the air to intercept a rocket at some point and save the world, yeah, you're going to want to use the 9.8. But we're not doing anything high-stakes rocket science in 8th grade. So you can just round it off to 10 and everyone will be happy. So back in Unit 1, when we learned about all the different kinds of measurements, we learned about length and distance, and we learned about weight. And we had a big discussion about how weight is different from mass and how the gram is used for mass, but the Newton is used for weight. Well, weight is actually the measurement of the force that is pulling down on you. It's the actual pull of gravity. When you're measuring weight, you're measuring how much the Earth is pulling down on you. Weight is a force. So anytime you have to calculate weight, you're going to want to use one of the force equations. Well, let's say you drop an object off a very tall building, or you decide to jump out of a perfectly good airplane. You will experience something called freefall. This is a vocab term. Freefall occurs when the only force that is acting on an object is gravity. So typically gravity is acting on you, like you're standing on the floor, you're laying on your bed. Whatever object that you are touching, what other object is that's supporting your weight, is actually pushing up against gravity. So gravity is pulling you down, and then you have this other force that's called normal force that's pushing up on you. So they balance each other out. It's a balanced system. Well, if you're actually falling towards the planet and there's nothing pushing back up on you, then you are in free fall. The only force that's acting on you in this case is gravity. And this is an unbalanced state, so since it's an unbalanced system of forces, you are going to change your speed. And in fact, you are going to accelerate. You are going to accelerate at 9.8 meters per second squared. All right, so note that when you actually drop something off of a high building or jump out of an airplane in real life, there is a large amount of fluid friction that exists between you, if you're falling through the air, and the molecules of the air. So as you are falling down, remember movement is now going down, friction always operates in the opposite direction of movement. So as you brush and go past all these air molecules, they're rolling, they're tumbling like past your body as you are going through them. There is a level of friction between you and all of these molecules. And this is what we would call a fluid friction because the medium that you're going through is able to flow. But it does slow you down, and that frictional force would be in the opposite direction. So this, though, makes the math really complicated. Really, you need to do some serious calculus and things like that to really solve the level of interaction between you and the molecules and all the friction. So for the most part, we just kind of eliminate this whole friction. We pretend it doesn't happen. And this is one of the problems sometimes that kids have when they start to get to physics and we start to work through free-fall problems. Because what we're going to talk about in class happening, you're going to look at in real life and go, but that's not the way it works. Well, that's because there's all these other factors in real life that we can't factor into the math. We don't have enough math skills to work it all out. We kind of have to pretend that some of these things don't exist. And one of the things that we pretend that doesn't exist is air friction. So when we talk about things in class or talk about things in the note videos and they don't seem to jive with what you would expect in the real world in physics, it's almost always because of friction, and it happens a lot when we do free fall things because of air friction. So you're going to need to know about it, but we're not really going to ever calculate it. All right, so here's a question, the first question in free fall problems. We'll say Billy has a mass of 60 grams. He jumps out of an airplane at an altitude of 10,000 feet. Well, how fast is he going to be falling after 2 seconds? How fast will he be falling after 4 seconds? So this is your basic speed equation, but one that uses acceleration. So if we have 2 seconds is the time times the acceleration, we can solve for speed. So 2 seconds times 10 meters per second squared. One of the seconds cancels out with one of the seconds, and we're left with meters per second. So after 2 seconds, Billy will be traveling 20 meters per second. Because if he started at 0, after second 1, he'll be going 10 meters per second. After second 2, he'll be going 20 meters per second. Well, after 4 seconds then, he'll be traveling 40 meters per second. And without any friction with the air, this would continue until the end, until he hit the ground, and he would just continuously accelerate an endless amount until he ran into the thing that he was accelerating towards, which would be the planet. Well, let's say Garrett has a mass of 75 grams. If we back up a little bit, that was more than Billy's mass, so he weighs more than Billy. He jumps out of the plane a second and a half after Billy. Well, how long until he catches up to him? This is one of the things that is a big misconception that students have. They think that heavier things, things with more mass, will fall faster, and that's just simply not true. There is a standard, there is a constant when it comes to free fall. It's because the force that's pulling down on you is dictated by the size of the planet, not the size of you. The force that you pull up on the planet is dictated by the size of you. All right, so while Billy, with his 60 kilogram body, would have a smaller amount of force than Garrett as far as the body's impact on the planet's impact on the two bodies is exactly the same. So that means that Garrett will never catch up to Billy. He's never going to. They're going to fall at exactly the same acceleration. So he will always be the exact same amount of time behind Billy. So he won't actually catch up to him until they both are on the ground. Well, how long after Billy hits the ground is Garrett going to crash into him? Well, if he jumped out of the airplane a second and a half after Billy, he's going to hit the ground a second and a half after Billy. All right, so how about a real math problem? How much distance will Garrett have traveled after 5 seconds of free fall? So you jump out of the airplane, you count 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. How far did you just fall? It's a fun thing to know how to do, and it has a lot of really interesting implications. You can figure out how deep a hole is. All you got to do, drop something down the hole and count. Well, if you know the rate that things fall, it's something you can figure out. You can turn that into distance. But here is a new formula that you need in order to do this. This is one of the free fall formulas. There will be several. Distance is equal to 0.5, or 1/2, times the acceleration of the object times time squared. So take note that this is more than just a free fall formula. This is a acceleration time distance formula, because this will also work if something is accelerating at a constant rate on a flat surface, or going up, or going in any direction that you want, in and out. It doesn't have to be free fall. Well, let's plug the numbers in. We're solving for distance still, so we don't have to rearrange anything. 0.5. The acceleration due to gravity is 10 meters per second squared times 5 seconds squared. So we have to square everything in the parentheses. We do that first because of order of operations. And that would then give us 25 seconds squared times 10 times 0.5. And it gives us 125 meters. You can work out all the other math separately if you're interested in it. But the second squared would cancel out the second squared. You'd be left with meters. As long as you do all of that, the math should work out very nice. So if you jump out of an airplane and count to 5, you will have fallen 125 meters closer to the surface of the Earth. Something that cracks me up, I used to do a lab. I used to do an activity where I would have the kids do experiments at home. And one of the ones that the kids would always choose to do would be drop things off of a deck or out of a window that had different masses. So in almost every time that the kids did this experiment, they would always bring back data that said that the heavier things fell faster than the lighter things, or that the heavier things hit the ground faster than the lighter things. Now, some of that's due to experimental error, as we learned with the ramp lab. You kind of sometimes have these misconceptions, and they show up in your data, even though it's not what really should be happening. And there's another level of this where they would drop things that air resistance would impact, like a flat piece of paper that would then kind of like settle down like a parachute, and a hard little stone that's going to fall straight, and they're kind of like setting up the experiment to fail. But the ones that would crack me up the most would be the ones that would tell me that they would drop two objects, and one of them would take 4 seconds to land the ground, and the other one would take like 7 seconds to land on the ground. It was just so obvious that they didn't actually do the experiment, and they were just making it up, because there's no way that their house is more than 125 meters tall. It used to always make me laugh. I would always write a note on it like, how big was that ladder? What if the plane's altimeter was wrong? What if Billy hit the ground after only falling for 10 seconds? We can use that information to figure out how high the plane is. So again, we are solving for distance. This time, though, instead of 5 seconds over here, it is 10. And we could figure out that the plane is flying 500 meters up in the sky. You should take the time to work this out. Use that formula that was on the last page, work it out, because it's the practice doing the math and solving these formulas that's going to help you the most when it comes time to do things on a test. All right, so what is going on with this air resistance? Well, it's a type of fluid friction. It gives an upward force to a downward falling object. And it is totally affected by surface area. When I used to give the project to the students and they would drop the things with different masses, one of the things that we would talk about that they would have to make sure that was the same, one of the variables, the most important variable to keep the same between the two objects, is the amount of surface area. If you're dropping two objects, a small object and a big object, it doesn't matter what their weight is, the big object is not going to fall as fast as the small because it has more surface area. There's going to be more friction with the actual air in real life. One of the things that I used to suggest would be to get two identical sized Tupperware containers. Put a bunch of pennies or something in one so that it was actually heavier than the other, but since they're exactly the same size, they would have exactly the same air resistance. And when you do that, you'll see that the objects will actually land at the exact same time. Another thing that we would theoretically talk about would be dropping two different sized bowling balls, an 8-pound bowling ball and a 16-pound bowling ball, for example. All bowling balls have to be exactly the same size. They're exactly the same size spheres. They're exactly the same amount of surface area, so the same amount of friction. But in general, the more surface area, the more resistance. Well, this makes sense because remember, you're falling through this fluid. You're falling through the gas. Things are flowing around you. So the more surface area you have, the more the molecules are going to rub against the outer part of the object that's falling. And the more rubbing, the more friction. Now, it's very useful if you're actually falling through the air because you don't want to just accelerate endlessly until you crash into the ground. When you deploy a parachute, that's how parachutes work. They work by dramatically increasing the surface area of you, the falling object, so much so that you can start to balance out the pull of gravity. You actually start to change the direction of the fall even. When you're falling, you're going straight down. When you pull that parachute, you convert some of that falling energy into a forward direction. You actually travel forward, like somewhere between 20 and 30 miles an hour. It's been a long time since I jumped out of an airplane. But somewhere between 20 and 30 miles an hour that you're actually moving forward when you're falling at the same time. Before you deploy that parachute, though, the faster that you are going, the more friction that there is. Well, this again makes sense because when you're falling faster and faster and faster, you're encountering more and more and more air molecules at a faster rate. So these air molecules are rolling over your body, you're flowing through them, and the faster you're going, the more of them you're encountering, the more of them you're rubbing against, so the level of friction goes up. This becomes very important because there reaches a speed at which the amount of friction that you are experiencing with the air completely negates the amount of force that the Earth is pulling down on you with. So when the upward frictional force equals the downward pull of gravity, you will stop accelerating because now you are existing in a balanced system again. Remember, there's two kinds of systems and forces. If there is an unbalanced system, that means that you have some kind of a force that's pushing on an object that's not countered by other things. That means you're going to have some kind of change in motion. You can change speed. You can have movement occurring that didn't occur before. It goes back to the Newton's laws. In this situation, once you are falling fast enough, then the friction balances out gravity, And you will just maintain that one speed, that constant speed. You will maintain due to Newton's first laws. In a balanced system, you will just continue doing what you're doing. Well, fun fact, terminal velocity for a human being, a typical human being, is about 52 meters per second. Now remember, this is entirely dependent on surface area. Nothing to do with weight, but surface area. Well, that's about 116 miles an hour. So if you were to go jump out of an airplane, the fastest that you can fall in real life is 116 miles an hour. So you jump out of an airplane, if you count to 6, you are no longer accelerating. You are now traveling really fast, over 100 miles an hour, hurtling towards the surface of the Earth. So, again, you should know the concept behind air resistance, but it would take pretty good level of calculus to actually work it into an equation if you want to find out with extreme accuracy exactly how far something is when it's falling. For the sake of argument for 8th grade, though, even if you did factor it in, it's only going to be off by a few centimeters, really, so it doesn't really matter in real life. Again, unless you're trying to shoot a missile out of the sky and save everyone. So, hope you enjoyed note video number 6. There is a booby trap. It is 14 questions, different kinds of free fall problems, calculating distances, calculating times, maybe changing it up with the pool of gravity, like if you went to a different planet. Enjoy, and don't forget to do the exit ticket.